let's talk about boundary behavior of waves. So what's a boundary? Well, that's where the media changes. So let's write a title here. Ooh, red. What is it? Boundary behavior. That is Peach. Yeah, Peach kept making it crash last year. I know where you're going with this. All right, so boundary is just it's just the interface between two mediums. So what we're going to do is we're going to try to show what that would look like. And the way to do it is to put a heavy medium. Let's try here. Yeah, that looks good. And let's make it attached to a lighter medium, say here. And let's have a wave travel through that heavier medium. Yellow, heavy. Okay, perfect. So now what this is meant to represent is the velocity of an incoming wave pulse, okay, and the side that it's on, okay? So this is a heavy to light scenario. This pen's a little on the thin side. Let's go this one, okay? And that means that we have a heavy cord going to a light cord. Now, a couple of interesting things about a heavier media. When we say heavier, like think of like a big heavy spring or a heavier rope attaching to a lighter rope. The number one thing to realize is that the velocity in the heavier rope will be lower than the velocity in the lighter rope. So if we have the velocity of the heavy, we're going to find that the velocity in the light will be higher, okay? This has a few implications, okay? We'll knock them out of the way first. So V equals F times lambda, okay? One thing that we know is if we were to send a train of waves in here, it would have a frequency, okay? The frequency of the wave is always set by the source. So it's set by source. So what that means is, as the waves come and they interface, some of the energy will be transmitted into the second cord, the lighter cord, but the frequency of the waves will stay exactly the same. So frequency is set. So what that must mean then is that if the velocity goes up, what has to happen to the wavelength in the new medium? It must also do what? Well, look at the math formula, right? If velocity goes up, frequency can't change. In order for this to stay true, something on this side must go up, and it has to be wavelength. Now I want you to understand why that's true. Frequency is set by the source. The frequency of waves will not change as the wave travels from medium to medium, okay? If they're coming faster here, and we're still registering the same wavelength we were here, then they must have a longer wavelength, seeing as how they're traveling faster but keeping the same frequency, right? The cycle has to take a little bit, well, has to take the same amount of time, and if they're hitting faster, then they must be longer to maintain that frequency. Does that make sense to you guys? I hope so. Okay, so now what we want to do is we want to take this, and we want to know what is going to happen after we go through the boundary, okay? So we can just move it all down here. And actually, let's just leave this, okay? So one thing that's going to happen is, remember that a wave represents input energy. And the more energy you have, the higher the amplitude, okay? So when this passes some energy into the new wave, and let's just draw that out. The thin wave here, looks like that. Okay, the new wave in the new medium, okay, is going to have a longer wavelength. It's not necessarily going to have a higher amplitude. That's to be debated, depending on the lightness it may. but it's going to be on the same side, okay? So what we'll have is we'll have a new transmitted wave. This is before, by the way. This is before the interface and this is after, okay? The reflected wave that comes back this way will be on the same side that it went in. The only difference is going to be that a bunch of its energy has been transmitted into the new wave, right? So it's going to appear with a much lower amplitude. Okay, so it's going to have a lower amplitude. Why? Because a bunch of its energy kept on going into the new medium. All right. So a few things to note here that are going to be important. The first thing is, if we're going from too big. If we're going from heavy to light, these are the things that happen. First thing is one, the transmitted wave that's this guy, the one that's transmitted into the new medium, the transmitted wave will A, have a higher velocity, and B, have a longer wavelength. And the proof for that, or the reasoning behind that, is this whole thing up here that we talked about. Frequency has to stay the same. Transmitted wave will A, have a higher velocity, and B, have a longer wavelength. And C, it will be on the same side, or it'll be in the same phase, if you want to be a little more technical, be the same phase. And two, the reflected wave will A, have a lower amplitude. Why? Because some of its energy kept on into the transmitted part of the, or into the transmitted wave. So have a lower amplitude, and B, be on the same side it came in on. And that is based on the fact that a heavy to light is more like a free end reflection. Free end reflections remain on the same side. Okay? Okay, here's our second scenario. This is a light to heavy wave, okay? And something I've also done here that you may have noticed is I've put in a wave with a strange shape. And that's just to illustrate another point as we're doing this. Okay, so this is light to heavy. This behaves more like a fixed end reflection, okay? So here's our incoming wave velocity. Remember, it's going to be faster in the light rope, slower in the heavy rope, okay? The question is, what does this look like upon, interface? So there's going to be some wave transmitted, there's going to be some wave reflected. Just give me a sec to draw that. Let's write in some stuff here. Okay, so here's a transmitted wave. Now remember, it's going slower. So now to keep the same frequency, what must have happened to the wavelength here? It must be shorter. It must be shorter, right? To keep the same frequency, it has to have shortened up. So we're getting the same number of waves in a given time for something that's traveling slower. There must be more of them, right? And then the reflected wave, what's going to happen is whichever part hits first is going to be the first part reflected back out. And there's going to be an inversion now, because this is more like hitting a solid end. So what you're going to have is you're going to have, what is going on? What you're going to have is apparently nothing. This. Okay, now there's going to be a much decreased amplitude, right? Because a lot of the wave energy went back this way. I'm sort of exaggerating. Probably in reality, you'd have a very little return, but just to illustrate the point we're showing this, okay? So we have the new transmitted wave moving along over here, right? And we have our reflected wave flying off backwards in the other direction. Whatever hit first reflects first. You have an inversion because it's light to heavy. So let's talk about this. So first of all, transmitted wave. Now this is light to heavy. Transmitted wave has a shorter wavelength. Why? Lower velocity. Has the same frequency if this were a wave train rather than just single wave pulses. The reflected wave is where all the interesting things happen. The reflected wave is inverted and has a lower amplitude. And one thing to always remember is whatever strikes first comes out first. So if you get a wave where you have to indicate like it's asymmetrical, make sure that whatever strikes first is drawn coming out first, right? So in other words, just first in equals first out on reflection. Okay, and that's it for reflection and transmittance between different media.